Now that we understand a black hole, let's talk about what would happen if we approached one. So at a great distance away from the black hole, nothing is weird. So for example, in this left image, this is part of the night sky, specifically in winter. Right here we have the constellation Orion. Right there we have the three belt stars. Number 2 up here, this is the star Betelgeuse, and the star marked as number 1, that's the brightest star in the night sky, Sirius. Notice I didn't say the brightest star, period. The brightest star in the sky is the sun, but the brightest star in the night sky is Sirius. Okay, so at a great distance, nothing looks weird. Now in this case, if we are going to be approaching a 3 solar mass black hole, then this is just around 3,000 kilometers away from the black hole. Okay, so that's continental US size. In other words, even that close, nothing's really appearing weird at all. Alright, but as we begin to get closer and closer, then we start to see the warping due to gravity. So this image over here on the right, this is an image of a black hole when we're around 30 kilometers away. Okay, so in other words, we're getting a lot closer. Now notice that the star positions have shifted. We know that the black hole is going to be here in the center, and we start to see the warping due to gravity. Okay, so here are the 3 belt stars. Up there's Betelgeuse, and down here's Sirius. So notice that all of those have moved. Now we also begin to see double images, meaning that the light from that star, as it goes around the sides of the black hole, gets bent, so now we see double images of the single object. So for example, there's Betelgeuse again. Down here's Sirius, there's Sirius again, there are the 3 belt stars, and over there are the 3 belt stars. Okay, the light is splitting around the black hole. Alright, here's our third lecture quiz question. What happens to light in a strong gravitational field? So in other words, we're standing in weak gravity, looking at light escaping from strong gravity. A, it is redshifted, B, it is blue shifted, C, it speeds up, or D, it slows down. Go ahead and think about it, and we'll discuss in just a bit. Alright, so what happens to light as it leaves strong gravity? It is A, it is redshifted. So again, the way I think about this is as the light is trying to escape, gravity's stretching it out, and as it stretches out, it becomes redshifted. It has longer wavelengths. Alright, and because I'm mean like this, here is our fourth lecture quiz question. What happens to a clock in a strong gravitational field? So we're standing in weak gravity looking at a clock running in strong gravity. A, it speeds up, B, it slows down, or C, it stays the same. Go ahead and think about it, and we'll discuss in just a bit. Alright, so a clock in strong gravity, the lengths, the space is getting bent a lot, which means that the time is going to slow down. So the correct answer is B, it slows down. Alright, so let's talk about something falling into a black hole. So we approached the black hole, now we're going to throw something in. In this case, we're going to use the blue test cube. This is why it was invented, was to be thrown in a black hole. So, at first, when it's far from the black hole near us, nothing's weird, it's still a cube, it's still blue, everything's fine. Then we throw it towards the black hole, and we begin to notice the redshift. So it used to be blue, but as it gets closer, it's going to shift to green, then yellow, then orange, then red. And then it's going to keep shifting to longer and longer wavelengths. This is still considered a redshift, but after red, it's going to go to longer wavelength of infrared, and then it will go to longer wavelength to microwave, and so on. Okay, so that's one thing we're noticing. Something else that is going to happen is that the gravitational pull from one side of the cube to the other side of the cube is going to get more and more different. In other words, we're going to have a stronger and stronger tidal force. what this is going to do is to cause the cube to begin to stretch out. So notice, far from the black hole, it's nice and cubey, but as it falls, it gets more and more stretched out. This is the process of spaghettification. This is an actual scientific term. Things spaghettify as they fall into a black hole. Now, something else we're going to notice is that time is going to slow. So as it gets closer and closer to the black hole, its time slows and slows and slows. And when it hits the event horizon from our point of view, its time will actually stop. We will never be able to see it cross the event horizon. However, by that point, its wavelengths will be so stretched out into the radio, we're never going to be able to measure them anyway. But technically, we'll never actually be able to see it cross the event horizon.